So this is problem 49 from chapter 26. So here we are given a circuit that I already drawn on the blackboard. It contains some resistors and some capacitor and a battery, and there is a switch. So all the resistors have the same resistance R. At t equals 0 with the capacitor C uncharged, the switch is closed. Now for part A, they are asking at t equals 0, the three currents can be determined by analyzing a simpler but equivalent circuit. Identify the simpler circuit and use it to find the values I1, I2, and I3, the three currents on the three branches of the circuit. And for part B, at t equals infinity, the currents can be determined by analyzing a simpler equivalent circuit. Identify the simpler circuit and implemented finding the values of I1, I2, and I3 at t equals infinity. And then for part C, they're asking at t equals infinity, what's the potential difference across the capacitor? Okay. So at t equals 0, the capacitor is completely uncharged. And the rule of thumb for those cases is that if you have an uncharged capacitor, then it acts as a short circuit. Okay? So the current is just going to readily pass through. Now to be sure, the current is not passing through. Some charge is accumulating on this side and corresponding negative charge is accumulating on this side. But when there is no charge on the plates of the capacitor, this just happens readily. Okay? As soon as some positive charge arrives here, this will induce some electric field and it's going to bring some negative charge on the other side of the capacitor. Okay? Once there is some charge accumulated, then this creates an inverse potential difference, and that's going to act like against the battery that's trying to charge the capacitor. Okay, but initially, because it's not charged, there is no potential difference across the capacitor. This acts as a short circuit. So at t equals 0, the capacitor is uncharged. This is the key point, okay? T equals 0 is not the key point. The key point is that the capacitor is uncharged. So at that charge, it becomes a short circuit. So the equivalent circuit is going to look like the switch is closed, there is a resistor here, or here, and there is a resistor here, and then we have a short circuit. We just go over this way. Okay? And there's going to be some R, and R. Those two R's are going to be an equivalent resistance of R over 2 because these are connected in parallel. And these are going to be an equivalent resistance of 3R over 2. So our potential difference provided by the battery is epsilon. So we can calculate the current, some I1, and I2 and I3 are going to be equal to each other because the circuit is symmetric, and I1 is going to be just their sum. Okay, and given the equivalent resistance and epsilon, the I1 is just going to be their ratio. So this is just epsilon over 3R times 2. Okay, so I1 is this. I1 and I2 is just half of this, epsilon over 3R each. Okay. Now for t equals infinity, their capacitor is fully charged. We are going to have the opposite effect. So this battery provided as much charge as it can provide to this capacitor, okay? And at that point, it can no longer charge this. And if you can no longer charge the capacitor, you can no more bring the charges to the two plates, then it acts like an open circuit. Okay? It's not letting current pass. It never lets the current pass, but there's not going to be a simulated current either. Okay? So there's no more positive charges coming here, negative charges coming here. So this is going to act like an open circuit. So this part of the circuit is going to be non-functional. Our circuit is going to be very simple. Some issue like this, okay, so the equivalent resistance is just going to be 2R, and the current I1 is going to be equal to E over 2R. Okay, then for part C, they're asking at t equals infinity, what's the potential difference across the capacitor? So let us introduce our capacitor again over here, but okay, let's make a new drawing, like so. Now there is no current passing through here. There is some current passing through. This I3 is 0 at t tending to infinity. Okay. Now what will be the potential difference across the capacitor in this case? Well, the potential difference across this resistor is 0. Okay. So the potential difference across the capacitor is in fact the potential difference across the non-current carrying resistor plus the capacitor over these two. But that one is equal to the potential difference across this resistor. And the potential difference across this resistor is going to be the potential difference provided by the battery divided by half, because half of that goes to potential difference over R, and the other half goes to potential difference over R. So this delta V is going to be equal to epsilon over 2. The delta V over here is 0, so this is epsilon over 2, this is epsilon over 2. Okay. By the symmetry of this problem, we can easily deduce that this is going to be epsilon over 2 as t tends to infinity. If these were not in fact symmetric, we would need to calculate the current and then multiply that current by the resistor over this side of the circuit and get our answer that way. And in fact, it gives the same answer. The current we calculated for this part was I2. That's epsilon over 2R. If you multiply it by the resistor on this part of the circuit, R, you get epsilon over 2. Okay? But the problem is so symmetric that you don't need to make any algebraic calculations for this one. If it was less symmetric, then you would need to refer to the current that you found in the previous part. Okay? So again, once again, if you have an uncharged capacitor, it is going to let the current pass through with no reaction, and so it's going to act like a short circuit. If the capacitor is fully charged, if it can no longer take any charge from the given circuit, then it's going to act like an open circuit. A capacitor, strictly speaking, can never be fully charged. If you increase the potential difference across it, and you're going to be able to load more charge onto it. What we mean by fully charged here is that fully charged for this circuit. So the circuit is now incapable of introducing more charge on the capacitor. Okay, so it's a property of the circuit, not the capacitor, or a circuit and the capacitor together. Right? But a capacitor, strictly speaking, by itself can never be fully charged, not an ideal capacitor. Okay? But when we reach that condition, when the circuit can no longer charge the capacitor further, then the capacitor starts acting like an open circuit. Okay? And that's the key to solving this problem.